Hello dear students of medical, non-medical and respected teachers. Today I am going to discuss the remaining two applications of Gauss's theorem. So first two applications I have discussed in applications of Gauss's theorem part 1. Now today applications of Gauss's theorem part 2. So third application, electric field due to a spherical shell. So if you have a charged spherical shell, then what will electric field at various points outside, inside, or at the surface of the shell? Suppose this is a spherical shell which is charged. Let Q be the total charge on the shell. Capital R is the radius of the spherical shell. Then sigma is equal to surface charge density of the spherical shell, that is charge per unit area. Now consider a Gaussian surface outside the shell, spherical Gaussian surface outside the shell, that is radius of this outer Gaussian surface is greater than the radius of the given spherical shell. Then electric field and ds vector will be in the same direction, that is radially outward, as electric lines of force are always normal to the charged surface. Another spherical shell or Gaussian surface inside the spherical shell of radius r, small r, less than capital R. So we have to find electric field inside the spherical shell, at the surface of spherical shell, as well as outside the spherical shell. So first of all, when point P lies outside the spherical shell, that is radius of the Gaussian surface is greater than the radius of the charged spherical shell, then E and ds are parallel to each other, that is angle between E and ds is 0. So therefore total electric flux at this point P, that is outside the spherical shell, is given by closed surface integral E dot ds, or it will be E ds cos 0, cos 0 is 1, or phi is equal to E closed surface integral ds, or closed surface integral ds of a sphere of radius small r is given by 4 pi r square. So flux will be E into 4 pi r square, equation number 1. Again, by using Gauss theorem, phi is also equal to Q upon epsilon naught, where Q is the total charge on the spherical shell. So comparing these two equations, we have E into 4 pi r square is equal to Q upon epsilon naught. So E comes out to be 1 over 4 pi epsilon naught Q upon r square. So this is equation number 3. So which is the required electric field due to a charged spherical shell at a point outside the shell. Second point, when P lies at surface of the shell. So if this point P lies on the surface of shell, then simply small r will be equal to capital R. So electric field becomes 1 upon 4 pi epsilon naught Q upon capital R square. But Q upon 4 pi r square, 4 pi capital R square is equal to sigma, which is surface charge density. So therefore E is equal to sigma upon epsilon naught C. So electric field due to a charged spherical shell at its surface is given by ratio of sigma, that is surface charge density, to epsilon naught. Third, when P lies inside the shell at this point, when P lies inside the shell, that is R is less than capital R, then electric field will be 0, because there is no charge inside the shell. So charge always reside on the surface of the outer surface of the shell. So there is no charge inside, it means there will be no electric field inside the spherical shell. So we have proved there is no field electric field inside the spherical shell at any point inside the spherical shell. Electric field at a point on the surface of the spherical shell is maximum and it decreases as we move away from the surface of the spherical shell. So we can plot a graph for electric field of a spherical charged spherical shell. So taking r long x-axis small r, electric field long y-axis. So inside the shell, when r is less than small r, E is equal to 0. There is no electric field. When r is equal to r, electric field becomes maximum. So maximum value of E. And when r is greater than r, E decreases and follows inverse square law. So electric field outside the spherical shell, charged spherical shell, follows inverse square law. So this is how electric field of a charged spherical shell varies inside at the surface and outside the spherical shell. Then last and fourth application of Gauss' theorem, electric field due to a parallel sheet of charge. There are two metallic parallel sheets of charges. Let positive charge on both say sigma 1 is the surface charge density of plate P, sigma 2 surface charge density of plate Q. So P and Q are two metallic sheets having surface charge density sigma 1 and sigma 2. Now there are three regions. Region 1 left to the left of this plate P, region 2 between P and Q, and region 3 to the right of plate Q. So we have to find electric field in three regions, first, second and third. Now that P1 is a point in the first region, P2 is a point in the second region, P3 is a point in the third region. Now we know that at P1, both electric field due to plate P and plate Q will be towards left in the same direction. E1 and E2 is electric fields at P1 due to charge at P and plate Q. Similarly, within the plates at P2, electric field due to P and Q will be opposite. And in region 3, electric field due to the plates P and Q will always be towards right and in the same direction. So now we can calculate electric field at P1 because we know the formula of electric field due to a sheet of charge E1, that is electric field in region first, is given by minus E1 plus E2 because they are in the negative direction. So they are added but sign is negative. So E1 is sigma 1 upon 2 epsilon naught that we have calculated plus sigma 2 upon 2 epsilon naught minus sign is taken outside, or 1 upon 2 epsilon is common minus sign, so sigma 1 plus sigma 2. It means in the region 1 to the left of plate P, electric field will be E1 will be equal to minus 1 upon 2 epsilon naught sigma 1 plus sigma 2, equation number 1. Similarly, at point P2, that is in the region between the two charge plates P and Q, E2 will be equal to E1 minus E2 because direction E1 is positive, E2 is negative. So electric field is subtracted. So it will be sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught, or 1 upon 2 epsilon naught sigma 1 minus sigma 2. This is electric field at point P2, equation number 2. Similarly, at point P3 in the region third, E3 will be equal to again E1 plus E2. Same direction, added, sign is positive. So E1 plus E2, it will be 1 upon 2 epsilon naught, sigma 1 plus sigma. So these are three electric fields in region first, second and third due to a set of two parallel metallic sheets. Now, special case. When sigma 1 is equal to plus sigma, sigma 2 is equal to minus sigma, as in case of capacitor. In the next chapter, in capacitor we take one positive plate and another is negative plate of same surface charge density. If sigma 1 is positive plus sigma 2 is minus sigma, then E1 will be equal to 0. because sigma 1, sigma and sigma 0. E2 will be equal to sigma minus sigma, that is sigma plus sigma, 2 sigma, 2 cancels, so it will be sigma upon epsilon naught. E3 will be equal to 0. It means for a capacitor having set of two parallel positive and negative charges of equal surface charge densities, electric field in the outside of the region of plates or to the left of plate P and to right of plate Q is always 0. There is no electric field outside these plates, and there will be constant electric field between the plates, which is given by sigma upon epsilon naught, which always goes from positive to negative plate. So this is all about electric field due to a set of parallel sheets. So this is all about applications of Gauss's theorem. So again, I remind you to subscribe my channel and watch my videos free of cost at your home. Be happy. All the best. Chardi Kala Raho.